What can we do now? What we can do now from this covariant form here is to replace H with its definition. H, I recall, is G minus NN, basically. G minus NN. So you have 1 over 2. G, the covariant derivative of G is 0, so you just have NN, N mu, N mu, plus H. Let us also replace here H by its definition. So we have, yes, we have a minus G minus N mu N rho partial nu rho N rho plus H nu rho, so that is G nu rho del mu N rho minus N nu N rho del mu N rho. So we already saw previously that these things are 0 because they are 1/2 del nu of n squared. So that is 0. And the rest we can rewrite. So we have 1/2. Let's apply the Leibniz rule, minus n rho del rho n mu n nu minus n rho del rho n nu n mu. And then this G can be taken inside the covariant derivative, so that's just del nu n mu. That we can write as H mu rho del rho n nu plus H nu rho del rho n mu. Why? Because if we apply the definition H is the delta. So from the two deltas you get the last two terms minus nn. So n mu, we have to check that the two terms we obtain there are the correct ones. And that is correct because they are the other two terms. But this is precisely k mu nu. Let's go back and check. We can also write k mu nu that way. And since it is symmetric, the other thing is k nu mu. So it is the same thing. So that is k mu nu plus k nu mu, but we have proven that it is symmetric, and that means that it is equal. The Lie derivative along the normal vector is equal to k mu nu. Now let sigma tau denote a family of submanifolds. So from one submanifold now we are considering a family parameterized by some time by some, you can call it time tau. Basically, what we want to do now is as follows. We want to consider, we will describe the boundary of our four manifold as the union of these the boundaries that you see here when we take the boundaries of this at infinity. So let's see, here you have sigma 1, let's see there you have sigma 2, let's see here you have sigma tau. Imagine this as space, sigma could be space, R3 evolving in time. But we compactify it somehow, so it's just a disk in this picture. Sigma 1 is the disk at time 1, and B is the boundary, the side boundary of this. And we will have points. Every point here we will see as flowing P1, point in sigma 1, flowing to a point in sigma tau, and then to a point in P2 in sigma 2. And we will describe M as the union in tau of sigma tau. So again, this is a picture where we will imagine M as the entire the manifold enclosed in this, but M is non-compact, so we will have to take the sigma 1 to minus infinity in time, sigma 2 to plus infinity in time, and B will become infinitely large to cover the entire R3. Anyway, this is called foliation of the manifold. Again, we assume that the manifold is described by some equation. By an equation chi, 1 for every tau. For example, we can imagine we can assume that this chi tau of x is some chi of x minus tau, which means that it is the same manifold chi of x. So the equation of sigma tau will be chi of x equal tau, which means that when you vary tau, this chi of x, instead of being 0, will be constant for every tau. So, for example, if your manifold is R3, chi of tau, chi of x could be t. T equal to tau is a 3 manifold, it's an entire space. When you have time and xy, and you choose time equal tau, some tau, you are just defining your manifold to be the plane, in this case R3. We don't need to be that specific for the moment, but just to make things less cryptic. And sigma 1 will be the sigma for tau equals to some tau 1, which we call initial time. Sigma 2 will be the same sigma at some time t2, tau 2, and that will be the final time. And in the end, we will assume that they are going to minus infinity and plus infinity respectively. So again, we do not work with R3 actually. This is just to illustrate, because we want to have something compact even in space, because we want to describe the boundary term of the action. And the boundary term of the action will be the sum of 3 integrals, one on this, one on that, and one on the rest. Then we can imagine that they are taken to infinity, but if we want to write them down explicitly, we need to imagine that they are compact. So let gamma x tau denote a curve such that at initial time it is a point on sigma 1, basically it is this curve. At final time it is a point of sigma 2, and at every time it is a point of sigma tau for every tau. So a curve that intersects the manifold sigma in 1 and 1 point for every tau. And imagine that you do the same for every point of sigma 1. Then you can define a flow so we have, first of all, we have x of tau is belonging to sigma tau, but sigma tau is described by that equation. So we have chi of x of tau minus tau equals 0. This defines a flow of diffeomorphisms that map your sigma from time t to tau to some other time. That map sigma tau in any sigma tau prime. Let us take this formula and differentiate it with respect to tau. So differentiating this formula with respect to tau, we get what? 0 is equal to 1 minus dx mu d tau gradient of x, calculated in x of tau. Now dx mu over d tau is the tangent to the surface, but the surface exits the submanifold. It's not tangent to the submanifold sigma, it's meant to exit, so it's kind of related to the orthogonal. And this is, we could define, so we could write this as 1 minus dx mu d tau 1 over lambda, the normal, and we could also define this as some delta mu n mu, where delta mu is this thing, which is a vector that has a component along the normal. So it's a vector that exits the surface. You could say, why don't we choose the normal? Well, because this is not the normal. This is any vector delta mu is a vector field that maps sigma tau in sigma tau plus d tau, let's say, infinitesimally. And you could take the normal, but this is not uniquely defined. We just need anything that is not uniquely defined. And we just need any delta mu such that delta mu n mu is different from 0. So that is the generator, if you want, of the flow. Any. And so taking a generic delta mu that such that this is non-zero, we decompose it in its component tangent to the surfaces and normal to the surface. Decompose delta mu in its components tangent to sigma and normal to sigma. So we define capital N mu as the component tangent to sigma, the components, and capital N as this product delta nu n nu. So this is delta mu minus n mu capital N, or if you want, you can write delta mu equals n mu plus small n mu capital N. This is tangent because it's orthogonal to the orthogonal. It's obtained by projecting. That's equal to, you see, h that's equal to h delta nu mu. Anyway, we can check directly that it is orthogonal to the orthogonal because n mu, small n mu, capital N mu is equal to this minus that, which is 0, because n squared is equal to 0. Okay, more concretely, let sigma tau denote the whole space at t equal tau. So that means that function chi of x is equal to t, as we said before. So that function chi of tau of x minus is equal to t minus tau. And what is del mu of x in this case? Chi, del mu of chi. If chi is t, that is just 1, 0, 0, 0. So we need something we need delta mu such that delta mu del mu chi different from 0. So we choose the simplest option, which is this. Time, that is generator of time evolution. Then what is the normal? The normal, remember, is lambda, some lambda, del mu chi. So there will be a lambda here, 0, 0, 0. The only difference between delta mu and the normal is a factor. Now, n mu is actually equal to capital N. This lambda is capital N. And we will call it that way from now on. Why? Because N, let's recall what capital N is delta nu and nu. And that's the product of these two things, so that's lambda. So we will write in this notation n mu as capital N 0, 0, 0. Where are we going here? We are going to parameterize the metric in a way that will, the 4x4 metric, in a way that will isolate the metric of the submanifold and the other components. So what is capital N mu? Capital N mu is delta minus n, here it is, delta mu minus n mu n. N that is 1, 0 minus n mu n. Let me, here you see this capital N is the 0th component of small n with lower index 0, just to say. Then we know that this product, small n, capital N, is 0. Let's write it here. 0 is this, but small n has only one component, so that is capital N, n 0. And that means the capital N 0 is 0. But capital N 0, we can read it from there, it's 1 minus small n 0 capital N. So that means that n0 with upper index is 1 over n. Okay, so capital N mu has no component 0, no 0 component. The other components will be called capital N I. But at the same time, from here again, this is equal to, well, 0. Okay, we have, see? The other ones are minus n I n from here. And that means that small ni is minus capital Ni divided by capital N. Now, H mu nu is equal to G mu nu minus N mu N nu. Let's see its various components. H00 is equal to G00 minus N lower index 0 squared. But N lower index 0 is capital N, so we have this. And we leave it there. H0i is equal to G0i because N mu with lower indices has no space components. Hij is equal to Gij. And Gij we will denote also with minus kappa ij, and for the signature, kappa ij we will call the metric of sigma submanifold. Now we know that n with lower indices, space indices, vanishes. But that is equal to Gi nu n nu, and that is gi0 n0 minus gij nj. n0 with the upper index is 1 over n, ni is minus ni divided by n. When we replace that, we have 1 over n gi0 minus gij capital N j, or gij is equal to hij or minus kij. This is h. But that is 0. So if that is 0, that means that g0i is equal to hij n j, or minus kij n j. Or we will write this as capital N with lower indices I. Remember, we will start lowering indices with the space metric, with the metric of the submanifold. Well, we are not done yet. N with upper index 0, we said is 1 over n, 1 over capital N. Good. But that is also equal to n mu g mu 0. However, n mu has only one component, which is capital N. So you have capital N g00, and that implies that g00 is 1 over n squared. Then we have that 1 is equal to n mu n mu, which can also be written as n mu g mu nu n nu. So this time we write it this way. And now we use that n mu, we could have written here, actually, because with upper indices, you have 1 minus ni. So here you have 1 divided by n squared, and then 1 gives g00, then you have minus 2 g0i ni plus gij capital Ni capital Nj. And this implies what? By multiplying by n squared, that implies that n squared is equal to this. That is g00 minus 2, you see g0i is minus ni with lower indices, so you have plus 2 ni ni. And then here you have that G is H, and Hn lowers the index with a minus. So you have minus n, I, n, I. So you can write G00 as n squared minus ni, ni. And finally, we can parameterize the metric with only objects that belong to that have indices that are raised and lower with the space portion of the metric itself. So G mu is what? G00 is this thing. G0I is that thing. And Gij is the metric. This is the parameterization that is commonly used for the metric. If you want, you can just say that, start from this result, you call this block Kij, you call that entry Ni, and then you call this N, you define that N to have G00 of this form. But if you do that, you lose the geometric meaning of this construction. Well, repeat that this capital N is what takes you outside the flows from one surface to the others. Let's see if we have time to compute the inverse. At least we write it down. The inverse is equal to 1 over n squared minus ni divided by n squared minus nj divided by n squared, and then here you have ni nj divided by n squared minus kij. Don't know if we have time to do it. If not, you will continue. If we check, so let's multiply, for example, this times that. So you have n squared 1 over n squared minus ni divided by n squared, and then you have plus ni divided by n squared. So this is correct. Let's do this one. So we did this. Let's do this times that. So we have minus nj divided by n squared minus kij, so plus kji ni divided by n squared but have to remember that this kappa is the metric that, apart from a sign, kappa now is a metric that with no sign, so it's correct, lowers and raises the indices, so this is 0. And then I leave it to you to continue and we can leave it there for today.